Take a look at this equation. It is not merely a collection of symbols on a page. It is a whisper from another reality. A reality that underpins our own. A world of shimmering probabilities and ghostly connections. This is the Schrödinger equation, the mathematical heart of quantum mechanics. It does not describe where a particle is, but rather the evolving, wave-like cloud of possibilities of where it could be, are. It is a map. Not of a fixed and solid territory, but of a hidden country of pure potential. A country where the familiar rules of our classical world dissolve into a beautiful and often unsettling strangeness. For decades, this equation was a tool for understanding, for peering into the subatomic realm and making sense of its bizarre behavior. But a new kind of dream has taken hold. A dream not just to understand the universe with this equation, but to build with it, to construct machines that do not just calculate, but that think in the very language of this quantum country. Machines that operate not on the rigid logic of ones and zeros, but on the fluid, superpositional logic of probability itself. These are not just faster computers, they are a new form of computation, a new way of interacting with the fabric of reality. They are a glimpse into how the universe truly works, and perhaps a glimpse into a future where we learn to work with it in ways we are only just beginning to imagine. The genesis of this radical idea can be traced back to the year 1980, to the mind of a physicist named Paul Benioff. In a world where classical computers were just beginning their inexorable march into every corner of our lives, Benioff imagined something fundamentally different. He conceived of a theoretical machine, a quantum Turing machine, that would operate not on the classical bits of information, the simple, binary on or off switches, but on qubits, tiny quantum systems that would obey the strange and wonderful rules of quantum mechanics. At the time, this was an idea that hovered in the borderlands between theoretical physics and science fiction. The practical challenge that gave it urgency was one that was becoming increasingly apparent to physicists: the profound difficulty of simulating the quantum world using classical machines. The problem was not a matter of processing speed, it was a matter of fundamental incompatibility. A classical computer, no matter how powerful, is a creature of certainty. It operates on a linear, step-by-step logic. But the quantum world is a creature of probability, of superposition, of entanglement. To fully simulate even a relatively simple quantum system, a molecule with just a few dozen atoms, for example, would require a classical computer to track an exponentially growing number of possible states. The computational resources required would quickly exceed the number of atoms in the entire observable universe. It was like trying to describe a rich, complex symphony using only the language of a telegraph key, a series of clicks and silences. The information was simply too rich, too multi-layered, to be captured by the limited binary language of the classical world. This fundamental challenge, this computational wall, was recognized independently by two of the great minds of 20th century physics, the Russian mathematician Yuri Manin and the American physicist Richard Feynman. Both arrived at the same radical conclusion. If you want to simulate a quantum system, you need a simulator that is itself quantum. You cannot hope to fully capture the richness of the quantum world using a classical machine. You must build a machine that operates on the same principles, a machine that speaks the same probabilistic language. Feynman, in a now legendary lecture in 1981, articulated this vision with his characteristic clarity and verve. "Nature isn't classical, damn it," he famously declared. "And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy." This was not just a complaint, it was a call to arms, an invitation to a new generation of scientists to think differently about the relationship between computation and the physical world. It was a suggestion that the very laws of physics could be harnessed not just to understand the universe, but to compute with it. The idea of a quantum computer was born, not as a tool for making our existing computers faster, but as a necessary tool for asking deeper questions of nature itself, for building a bridge into the strange and beautiful quantum country that Schrödinger's equation had first mapped out for us. It was a dream of a machine that would be not just a product of human ingenuity, but a true collaborator with the cosmos. In the year 1984, just a few years after Feynman's visionary call to arms, the strange and beautiful principles of the quantum world made their first decisive leap from the esoteric realm of theoretical physics into the practical world of human affairs. This leap was not in the form of a computer, but in something equally revolutionary, a new form of secret keeping. The physicists Charles Henry Bennett and Gilles Brassard, inspired by the deep and often paradoxical nature of quantum measurement, realized that the very fragility of the quantum world, its inherent sensitivity to observation, could be turned into an unbreakable shield for communication. They developed a protocol, now known as quantum key distribution, or QKD, that could create a cryptographic key that was not just computationally difficult to crack, but physically impossible to intercept without being detected. It was a technology that turned the laws of quantum mechanics into the ultimate security guards. To understand the genius of their idea, imagine two people, let's call them Albert and Catherine, who wish to share a secret message. They know that a malevolent eavesdropper, Ella, may be listening in on their communication channel. In classical cryptography, Albert would encrypt his message using a mathematical key, and Catherine would use the same key to decrypt it. The security of this system relies on the secrecy of the key, but if Ella can intercept the key as it is being transmitted, the entire system is compromised. Bennett and Brassard's protocol solves this problem by using quantum mechanics to transmit the key itself. Albert sends Catherine a string of individual photons, the quantum particles of light. Each photon is prepared in a specific quantum state, a state of polarization, which represents a single bit of the secret key, a 0 or a 1. The magic and the security lies in the fundamental act of quantum measurement. If Ella tries to intercept these photons to read the key, she is forced to make a measurement. And as we know from the double-slit experiment, the very act of measuring a quantum system inevitably disturbs it. Her observation will collapse the photon's wave function, altering its polarization state in a subtle but detectable way. After the transmission is complete, Albert and Catherine get on an open public channel and compare a randomly chosen subset of the photons they sent and received. They do not reveal the key itself, only the settings they use to measure the photons. If their results match perfectly, they can be confident that no one has been listening in, and that the remaining undiscussed photons constitute a perfectly secret key that they can then use to encrypt their message using a classical one-time pad cipher. If, however, they find discrepancies in their results, they know that Ella has been eavesdropping. The act of her measurement has left an unavoidable quantum footprint. They can then discard the compromised key and start the process over again. This is a security system of a completely new kind. Its security is not based on the mathematical difficulty of solving a problem which could one day be broken by a more powerful computer. Its security is guaranteed by the fundamental laws of physics. The universe itself conspires to protect their secret. Any attempt to gain information about the key inevitably creates a disturbance, a trade-off that is hardwired into the very fabric of reality by the uncertainty principle. Bennett and Brassard's work was a watershed moment. It was the first concrete demonstration that the strange and seemingly paradoxical features of the quantum world were not just a source of philosophical debate for physicists, but could be harnessed to create powerful new technologies with real-world applications. It proved that quantum mechanics was not just a descriptive theory, confined to the sterile environment of the laboratory. It was a prescriptive one, a set of rules that could be used to build, to engineer, and to create. Today, quantum key distribution is no longer a theoretical curiosity. It is a rapidly developing technology, with secure quantum communication networks being built and tested around the world. It is being used in sensitive industries, from government and military communications to financial transactions and data centers, to protect our most valuable information from the prying eyes of both present-day hackers and future powerful quantum computers. The story of QKD is a beautiful and powerful example of how a deep theoretical insight into the fundamental nature of reality can lead to a technology that has a profound and lasting impact on our society. It is a testament to the fact that the quest to understand the universe, in all its strangeness and beauty, is not just an intellectual pursuit. It is the very engine of human progress. The unbreakable code of quantum cryptography is not just a technological marvel. It is a philosophical statement, a declaration that in the deep, probabilistic, and observer-dependent reality of the quantum world, some secrets, at least, can be kept forever. The classical computers that power our modern world are, without a doubt, one of the most transformative inventions in human history. They are monuments to our ability to manipulate logic, to control the flow of electrons with exquisite precision, and to build systems of immense complexity. From the intricate simulations that predict our weather to the vast interconnected network of the Internet, from the life-saving diagnostics of medical imaging to the simple act of watching this video, our lives are woven into the very fabric of classical computation. But for all their power, these machines are fundamentally limited. They are creatures of a classical, deterministic world, and they think in a language that is profoundly different from the native language of the universe itself. At their heart, classical computers process information in bits, tiny, physical switches that can be in one of two definite states, a 0 or a 1, an off or an on. Every calculation, no matter how complex, is ultimately broken down into a long, sequential series of these simple, binary operations. When a classical computer simulates the folding of a protein, it is translating the complex quantum mechanical interactions of thousands of atoms into a vast, but ultimately linear, sequence of ones and zeros. When it renders a photorealistic image in a video game, it is performing a massive number of simple, geometric calculations, one pixel at a time. It is a process of immense speed and precision, but it is fundamentally a process of brute force, of solving a problem by marching through all the possible steps, one by one. This approach works remarkably well for a vast range of problems, but there is a class of problems. A class of problems that often holds the key to our deepest scientific and technological challenges, where this linear, step-by-step approach fails catastrophically. These are problems whose complexity grows exponentially with the size of the system. The simulation of a quantum molecule is a prime example. For each new electron you add to the simulation, the number of possible quantum states that the system can be in doubles. The complexity of the problem explodes. For these kinds of problems, even the most powerful supercomputer on Earth is like an abacus trying to calculate the trajectory of a rocket to Mars. It is not just a matter of making the computer faster. The problem itself is of a different order of complexity. It is a problem that requires a different kind of thinking. Quantum computers are not just a faster version of classical computers, they are a fundamentally new kind of machine, a machine that thinks in a fundamentally new way. They are designed to speak the native, probabilistic language of the quantum world. They process information not in bits, but in qubits. A qubit is not a simple on or off switch. It is a tiny quantum system, An atom, an ion, a photon, a superconducting circuit that can exist, thanks to the principle of superposition, in a combination of both 0 and 1 at the same time. It is not either 0 or 1. It is a weighted blend of both. This single, simple difference is the source of all of a quantum computer's power, because a qubit can be both 0 and 1 simultaneously. A quantum computer with just a few qubits can explore a vast computational space. In a single step, a 2-qubit system can be in a superposition of 4 states. A 3-qubit system can be in 8 states. The number of states grows exponentially. A quantum computer with just 300 qubits could, in principle, represent more possible states simultaneously than there are atoms in the entire observable universe. This is a computational space of truly cosmic proportions. To understand the power this gives, imagine trying to find your way through a vast, complex maze with a single, correct path. A classical computer is like a person walking through the maze, trying each path one by one, hitting a dead end, backtracking, and trying another. It is a slow, painstaking, sequential process. A quantum computer, on the other hand, is like a flood of water that is poured into the maze. The water flows down all possible paths simultaneously. By observing where the water comes out, you can instantly determine the correct path. This is the power of quantum parallelism, the ability to perform a massive number of calculations at the same time. But the magic of quantum computing does not stop with superposition. It also harnesses the strange and powerful phenomenon of entanglement. When qubits become entangled, their fates become linked, no matter how far apart they are. The state of one qubit instantly influences the state of another. This creates a deep, non-local connectivity within the quantum computer, allowing for complex correlations and information processing that are impossible in a classical machine. It is as if the different parts of the computation are in constant, instantaneous communication with each other, sharing information and working together in a holistic, coordinated way. It is this combination of superposition and entanglement that gives quantum computers their potential to solve certain specific classes of problems that are intractable for any classical computer. These are not everyday problems, like sending an email or streaming a video. They are the deep, hard problems at the frontiers of science and technology, simulating the behavior of new molecules for drug discovery and materials science. Solving complex optimization problems in logistics and finance, and, most famously, breaking the cryptographic codes that protect our digital world. A quantum computer is not a universal problem solver, but for the right kind of problem, it is a tool of almost unimaginable power, a tool that allows us to tap into the vast, hidden computational resources of the quantum realm itself. The potential of quantum computers to revolutionize our world is perhaps most starkly illustrated in the field of cryptography. Our modern digital economy, from online banking and e-commerce to secure government communications, is built on a foundation of public key cryptography, most famously the RSA algorithm. The security of this system relies on a simple but profound mathematical asymmetry. It is very easy to take two large prime numbers and multiply them together, but it is incredibly computationally difficult to take their large product and find the original two prime factors. A classical computer, even a supercomputer, would have to resort to brute force methods, trying all possible prime factors one by one. For the large numbers used in modern RSA encryption, this process would take a classical computer longer than the age of the universe. This mathematical difficulty is the lock that protects our most sensitive digital information. But in 1994, a mathematician named Peter Shor, then working at Bell Labs, discovered a quantum algorithm that could pick this lock with ease. Shor's algorithm is a beautiful and ingenious piece of mathematics that shows how a quantum computer could find the prime factors of a large number exponentially faster than any known classical algorithm. It does this by cleverly using the principles of quantum parallelism and interference. A quantum computer running Shor's algorithm can, in a sense, test a vast number of potential factors simultaneously. It then uses a technique called the quantum Fourier transform to create an interference pattern in the probabilities of the different outcomes. A pattern that reveals the period of a certain mathematical function, which in turn allows for the efficient calculation of the prime factors. The details are complex, but the upshot is simple and profound. A sufficiently large and stable quantum computer could break most of the public key cryptography that we rely on today, rendering our current standards of internet security obsolete. This is not a distant, theoretical threat. It is a very real and pressing concern for governments, corporations, and security agencies around the world. The race is now on to develop new, quantum-resistant or post-quantum cryptographic algorithms that are secure against attacks from both classical and quantum computers. This is a fascinating, high-stakes game of cat and mouse, a computational arms race between the code breakers and the code makers. But the power of quantum computing extends far beyond the realm of cryptography. It has the potential to revolutionize a vast range of fields that are currently limited by the computational complexity of the problems they face. In medicine and drug discovery, for example, designing a new drug often involves simulating how a potential drug molecule will interact with a target protein in the body. This is a quantum mechanical problem of immense complexity, and classical computers can only provide rough and often inaccurate approximations. A quantum computer could, in principle, simulate these molecular interactions with perfect accuracy, allowing for the rapid, rational design of new, more effective drugs for a vast range of diseases, from Alzheimer's to cancer. In materials science, a similar logic applies. The properties of a new material, its strength, its conductivity, its magnetism, are determined by the quantum mechanical behavior of its constituent atoms and electrons. A quantum computer could allow us to design new materials from the ground up to create, for example, a room temperature superconductor, a highly efficient catalyst for clean energy production, or a new type of battery with unprecedented energy density. The possibilities are almost limitless. And in the field of optimization, quantum computers could find solutions to some of the most complex logistical problems that plague our modern world. Imagine a quantum algorithm that could optimize the entire global supply chain in real time, reducing waste and increasing efficiency, or one that could solve the traveling salesman problem for a vast network of delivery trucks, finding the most efficient routes and saving immense amounts of time and fuel. Or one that could design new, more efficient financial models for managing risk and optimizing investment portfolios. These are all problems that, in their full complexity, are beyond the reach of classical computers. But they are problems that are perfectly suited to the unique, parallel, and holistic problem-solving capabilities of a quantum computer. The quantum age is still in its infancy, but the promise is clear. We are on the verge of a new computational paradigm, a paradigm that will not just make our computers faster, but will allow us to ask and to answer a new class of questions. Questions that touch on the very foundations of chemistry, of biology, of finance, and of our ability to create a more efficient, more sustainable, and more intelligent world. The promise of quantum computing is so immense, so transformative, that it is easy to get carried away by the hype. It is tempting to see these machines as a kind of technological panacea, a magical solution to all of our most difficult problems. But the reality, as is so often the case in science, is far more nuanced, more challenging, and in many ways, more interesting. Quantum computers are not, and will never be a universal fix for all of our computational needs. In fact, for the vast majority of the tasks that we use computers for in our everyday lives, they are completely and utterly useless. Checking your email, browsing the web, editing a document, playing a video game. These are all tasks that are perfectly suited to the deterministic, sequential logic of a classical computer. A classical computer excels at executing a long series of simple, well-defined instructions, and it does so with incredible speed and reliability. A quantum computer, on the other hand, is not designed for these kinds of tasks. It is not just that it would be overkill, it would be profoundly impractical. It is like using a delicate, $1 million Formula One racing car to go to the grocery store. It is the wrong tool for the job. The very power of a quantum computer, its ability to exist in a superposition of multiple states, is also the source of its greatest challenges. When you measure the result of a quantum computation, you do not get a single, definite answer. The act of measurement collapses the quantum state, and what you get is a probabilistic outcome. The wave function gives you the probabilities of the different possible answers, but the specific answer you get in any single run of the experiment is fundamentally random. This means that to get a reliable result, you often have to run the same quantum computation many times and build up a statistical distribution of the outcomes. The genius of quantum algorithms, like Shor's algorithm, is that they are cleverly designed to use quantum interference to amplify the probability of the correct answer and to cancel out the probabilities of the wrong answers. But this is a highly non-trivial task, and it is only possible for a very specific class of problems. For most problems, the raw parallel processing power of a quantum computer is simply lost in a sea of randomness. The second, and perhaps even greater, challenge is the profound fragility of the quantum state itself. The qubits that make up a quantum computer are incredibly, exquisitely sensitive to their environment. They are like tiny, delicate soap bubbles, existing in a fragile state of quantum coherence. Any stray interaction with the outside world, a single photon of light, a tiny vibration, a fluctuation in the ambient magnetic field can act as an unwanted measurement, causing the delicate superposition to collapse in a process called decoherence. When this happens, the quantum information is lost and the computation fails. This is the great enemy of quantum computing. To protect their qubits from decoherence, quantum computers must be built and operated under the most extreme conditions imaginable. They are housed in complex, multi-layered cryostats that cool them down to temperatures just a few millikelvin above absolute zero, colder than the deepest reaches of outer space. They are shielded from all forms of electromagnetic radiation and mechanical vibration. Maintaining these conditions is an immense scientific and engineering challenge, and it is what makes current quantum computers so large, so expensive, and so difficult to scale up. And even with all these precautions, errors are still inevitable. The qubits themselves are not perfect, and the control pulses used to manipulate them are not perfectly precise. This leads to a constant stream of errors that must be corrected. The theory of quantum error correction is a beautiful and sophisticated field of research, but it comes at a very high price. To create a single, stable, logical qubit that is protected from errors, you need to use a large number of physical qubits, perhaps hundreds or even thousands, to encode the information in a redundant way and to constantly monitor and correct for errors. This means that the number of physical qubits required to build a useful, fault-tolerant quantum computer is far, far greater than the number of logical qubits needed for the computation itself. To run Shor's algorithm to break RSA encryption, for example, might require a few thousand logical qubits, but with the overhead of error correction, this could translate into a machine with millions of physical qubits. We are currently in an era of noisy intermediate-scale quantum devices, machines with a few dozen to a few hundred physical qubits that are not yet protected by error correction. These are powerful and exciting research tools, but they are a long way from the large-scale, fault-tolerant machines of our dreams. Companies like Google, with its Sycamore processor, and Rigetti, with its Aspen platform, are at the forefront of this research, using their NISQ devices to explore the frontiers of quantum chemistry and machine learning. But the path to a truly universal, fault-tolerant quantum computer is a long and arduous one. And finally, it is important to remember that quantum computers are highly specialized machines. They are not general-purpose computers. They are designed to excel at a very specific set of tasks, those that can exploit the unique properties of quantum mechanics, like factoring and optimization. For a vast range of other problems, a classical computer will always be the faster, more efficient, and more practical tool. The future of computing is not a future where quantum computers replace classical computers. It is a future of hybrid computing, a future where classical and quantum computers work together, each playing to its own strengths. The classical computer will handle the control, the data input and output, and the parts of the problem that are classically easy, and it will hand off the hard quantum part of the problem to the quantum coprocessor. Quantum computers are not the answer to everything, but they are the answer to some of the most profound and important questions we face. They are not tools for making our everyday lives more convenient. They are tools for expanding the very boundaries of human knowledge, for simulating the universe, for discovering new drugs, for creating new materials, and for unlocking the deepest secrets of nature itself. They are not tools for the ordinary, they are tools for the extraordinary. The relationship between the two most transformative and disruptive technologies of our time, quantum computing and artificial intelligence, is a subject of immense interest, speculation, and often confusion. On the one hand, we have the strange, probabilistic, and mind-bending world of quantum mechanics, a world that even its founders famously claimed not to understand. If you are not shocked when you first come across quantum mechanics, Niels Bohr is reputed to have said, "You cannot possibly have understood it." Erwin Schrödinger, whose equation is the very bedrock of the theory, once lamented, "I do not like it, and I am sorry I ever had anything to do with it." This is a theory that challenges our deepest intuitions about reality. And yet, from this strange and unsettling foundation, we are now building machines of almost unimaginable power. At the same time, we are witnessing the explosive rise of artificial intelligence, particularly in the form of deep learning. AI is a technology of a very different flavor. It is not built on the strange paradoxes of a fundamental theory, but on the pragmatic and powerful idea of learning from data. An AI system, like DeepMind's AlphaFold, which solved the 50-year-old grand challenge of protein folding, does not work from first principles. It is trained on vast data sets, and it learns to recognize patterns and make predictions with a level of accuracy that can often surpass human experts. AI is fast, it is adaptable, and it is surprisingly, and sometimes unsettlingly, good at solving problems that we once thought required human intuition. It is natural, then, to ask how these two powerful technologies will interact. Will they be competitors or collaborators? The initial hype around quantum computing often positioned it as the ultimate problem solver, a machine that would render even the most powerful AI systems obsolete. The argument was that many of the hard problems in AI, particularly in machine learning and optimization, are computationally complex, and a quantum computer, with its ability to explore a vast space of possibilities simultaneously, would be the perfect tool to solve them. This has given rise to the field of quantum machine learning, which seeks to develop quantum algorithms that can speed up tasks like classification, clustering, and optimization. But the story, as is so often the case, is more complex. As AI has become more powerful and sophisticated, It has begun to encroach on territory that was once thought to be the exclusive domain of quantum computers. By training on huge data sets of physical simulations and by incorporating the known laws of physics into their neural network architectures, some AI systems have shown that they can find highly accurate, approximate solutions to complex quantum problems, often much faster and more efficiently than a current, noisy quantum computer could. The CEO of DeepMind, Demis Hassabis, has suggested that for many practical problems in fields like drug discovery and material science, a clever AI running on a powerful classical computer might be able to find a good enough solution, potentially reducing the need for a full, fault-tolerant quantum computer. This does not mean that quantum computing is a dead end. There are still classes of problems, like factoring large numbers, where a quantum computer is provably exponentially faster than any classical algorithm. But it does suggest that the quantum advantage, the point at which a quantum computer can solve a practical, real-world problem better than any classical computer, may be a more subtle and harder-to-reach target than was once thought. The real story, however, is not one of competition, but of synergy. The future is not about quantum computing versus AI, it is about quantum computing and AI. These are not two competing technologies, but two complementary tools, two different ways of thinking that, when combined, could be far more powerful than either one alone. Imagine a hybrid workflow for discovering a new drug. An AI system could be used to sift through a vast database of millions of potential drug molecules, using its pattern recognition capabilities to identify a few promising candidates. This is a task that AI is perfectly suited for. But then, to truly understand how these candidate molecules will interact with a target protein, to calculate their binding energies with high precision, you need a full quantum mechanical simulation. This is the part of the problem that is classically hard, and it is where a quantum computer would excel. The AI would do the broad, exploratory search, and the quantum computer would do the deep, precise analysis. It is a partnership, a collaboration between two different kinds of intelligence. AI can also play a crucial role in the development of quantum computers themselves. The task of controlling a quantum computer, of calibrating the thousands of delicate control pulses needed to execute a quantum algorithm, is an immensely complex optimization problem. An AI system can be trained to learn the optimal control sequences, to find the best way to tune the machine to minimize errors and maximize performance. In a sense, we are using AI to learn how to speak the language of the quantum world, to find the right words to command our fragile, powerful new machines. This synergy is already being explored in laboratories around the world. Google, for example, with its new Willow quantum chip, is making significant strides in the crucial area of quantum error correction. The Willow chip, with its 105 qubits, is designed to test and improve error-correcting codes, a key step on the road to a fault-tolerant quantum computer. The challenge of error correction is not just about building better hardware. It is also about designing smarter codes and more efficient decoding algorithms, a task where the pattern recognition capabilities of AI could be invaluable. The future, then, is not a simple one of quantum supremacy or AI dominance. It is a more complex and more interesting future of coevolution. Quantum computing provides a new, powerful tool for solving the most difficult computational problems in science, while AI provides a new, powerful tool for learning from data and for controlling complex systems. Together, they are a formidable combination, a partnership that has the potential to accelerate the pace of scientific discovery and technological innovation in ways that we are only just beginning to comprehend. The story is not about one replacing the other. It is about figuring out where each excels and how they can be woven together to create a computational fabric that is far richer and more powerful than anything we have ever seen before. The idea that the universe itself might be a kind of quantum computer is one of the most profound and mind-bending concepts to emerge from the intersection of physics, computer science, and cosmology. It is a perspective that reframes our entire understanding of reality, suggesting that the cosmos is not just a collection of matter and energy evolving according to physical laws, but is an active, ongoing computation, a process of information being transformed and manipulated at the most fundamental level. The physicist Seth Lloyd, one of the pioneers of quantum computing, was one of the first to articulate this idea in a clear and compelling way. He argued that every interaction between elementary particles, every collision, every decay, every quantum jump, can be seen as a fundamental computational operation. The universe, in this view, is constantly computing its own future state, moment by moment, through the ceaseless, parallel interactions of all its constituent parts. This is not just a loose metaphor. The principles that govern the universe at its most fundamental level, superposition, entanglement, interference, are the very same principles that we are now harnessing to build quantum computers. A quantum computer does not solve problems in the linear, step-by-step fashion of a classical machine. It evolves a quantum state, exploring a vast superposition of possibilities simultaneously, until it settles into a final state that encodes the solution. This is remarkably similar to how the universe itself seems to operate. The wave function of the universe contains a superposition of all possible histories, all possible configurations of matter and energy, and the reality we experience is the result of this universal wave function evolving and collapsing according to the laws of quantum mechanics. It is as if the cosmos is running a massive cosmic program, a program whose output is the reality we observe. This perspective gains a new and tangible significance in light of recent experiments, like the one conducted in late 2022 on Google's Sycamore quantum processor, which simulated the behavior of a traversable wormhole. This was not, of course, the creation of a physical tunnel through space-time, but it was a stunning demonstration of the deep connection between the physics of quantum information and the physics of gravity. The experiment was based on the holographic principle, a profound and counterintuitive idea from string theory and quantum gravity, which proposes that a theory of gravity in a certain number of dimensions can be equivalent to a quantum field theory without gravity in one fewer dimension. It is as if our three-dimensional universe, with all its gravitational complexity, could be a holographic projection of a simpler two-dimensional quantum system living on its boundary. The wormhole simulation on the Sycamore chip was a laboratory test of this ADS-CFT correspondence, as it is technically known. The researchers created a highly entangled state of a few qubits on their quantum processor, a state that was mathematically equivalent via the holographic duality to a simplified model of two black holes connected by a wormhole. They then dropped a piece of quantum information into one of the black holes on the chip and watched as it scrambled and spread throughout the system, only to re-emerge, perfectly intact, from the other black hole. The information had, in a sense, traversed the simulated wormhole. This was a landmark experiment because it was the first time that a phenomenon with gravitational properties had been observed to emerge from a purely quantum system. It provided a powerful, albeit circumstantial, piece of evidence for the holographic principle and for the deep underlying connection between quantum entanglement and the geometry of space-time. It suggests that the very fabric of our universe, the smooth, continuous space-time of Einstein's gravity, may be an emergent property of the strange, non-local connections of a vast underlying quantum system. Entanglement, in this view, is not just a strange quirk of the quantum world. It is the very thread from which the tapestry of space-time is woven. If the universe is indeed a giant quantum computer, then the implications are staggering. It reframes our entire scientific endeavor. We are not just external observers, discovering the pre-existing laws of a mechanical universe. We are parts of the computation itself, self-aware substructures that are beginning to understand the logic of the program we are running in. The laws of physics are not just a set of external rules, they are the algorithm. And by building quantum computers, we are not just creating powerful new tools. We are, in a very real sense, learning to speak the universe's native language, to write our own subroutines in the cosmic code. The wormhole simulation is just the beginning. In the future, quantum computers could be used to simulate the quantum chaos inside a black hole, to probe the nature of the Big Bang singularity, to understand the properties of dark matter, or to explore the landscape of possible universes predicted by string theory. They could become our ultimate tool for exploring the frontiers of fundamental physics, a way to create and study toy universes in the laboratory, to test our most ambitious and speculative ideas about the nature of reality. This perspective also offers a new way to think about the complexity of the universe. The sheer, overwhelming complexity of a biological organism, of an ecosystem, of a conscious brain, can seem almost miraculous, almost impossible to have arisen from simple, random processes. But if the universe is a quantum computer, then it is a complexity-generating machine of almost infinite power. The parallel processing capabilities of the cosmos are constantly exploring a vast space of possibilities. And the emergence of complex and ordered structures may be a natural and even inevitable outcome of this cosmic computation. But this grand vision must be tempered with a dose of humility. A humility that comes from confronting the true, unimaginable scale of cosmic complexity. The notion that we could one day build a quantum computer that could simulate the entire universe is a form of computational hubris. The universe is, by definition, the most powerful computer it is possible to build for simulating itself. Any computer we build within the universe will, of necessity, be a smaller, and therefore less powerful, part of the whole. The wormhole experiment on the Sycamore chip did not simulate a real astrophysical wormhole. It simulated a highly simplified toy model, a model that was specifically designed to be simple enough to run on a few noisy qubits. This is a crucial point, and it brings us to a deep and often overlooked aspect of the relationship between computation, complexity, and our own human cognition. The universe may be a quantum computer of infinite capacity, but our own minds, and the computers we build as extensions of our minds, are finite. We are, and will always be, dealing with a sliver of reality, a manageable approximation of an infinitely complex whole. The universe, in its raw, untamed reality, is a place of almost infinite complexity. The number of possible ways that the particles in even a small volume of space can be arranged is a number so vast that it dwarfs any number we have ever encountered in our everyday lives. And yet, we, as human beings, have a powerful, and perhaps necessary, cognitive bias towards simplicity. We are pattern seekers, storytellers. We look for the simple laws, the elegant equations, the coherent narratives that can make sense of this overwhelming complexity. This is the very essence of the scientific endeavor. But in this search for simplicity, we must be careful not to mistake the map for the territory, not to assume that the universe itself is as simple as our models of it. This is a point that is beautifully illustrated by a simple, but profound, thought experiment involving coin flips. If you flip a coin 20 times, the number of possible sequences of heads and tails is 2 to the power of 20, which is just over 1,000,000. The chance of you getting any one specific sequence is 1 in 1,000,000. If you flip the coin 266 times, the number of possible sequences is 2 to the power of 266, a number that is larger than the estimated number of atoms in the entire observable universe. The vast, overwhelming majority of these sequences will look, to our pattern-seeking eyes, completely random, a meaningless jumble of heads and tails, but a few of them will have a simple, recognizable pattern: all heads, all tails, alternating heads and tails. Our minds are immediately drawn to these simple, ordered sequences. We see them as special, as significant, but from a purely probabilistic point of view, the sequence of all heads is just as likely, or rather, just as unlikely, as any other specific, random-looking sequence. Our bias for simplicity is a cognitive illusion. We live in a universe that is, for the most part, irreducibly complex. But our minds are designed to pick out the rare and often illusory islands of simplicity. This has profound implications for how we think about computation, both classical and quantum. A computer, at its core, is a machine for generating sequences of bits, but a classical computer will never, and can never, produce every possible sequence of bits. It is designed to follow a specific, deterministic algorithm, a simple, manageable path through the vast, untamed wilderness of computational possibility. We build our computers to solve the problems that we, with our simplicity-biased minds, have learned how to solve. We keep them on a narrow, well-trodden path because it is the only path we know how to navigate. We often think of computers as being magical, complex machines. But in a deep sense, they are engines of radical simplification. They work because we have forced them to ignore the overwhelming complexity of the real world and to operate in a tightly controlled, logical, and simple sandbox. The same is true, in a different way, for quantum computers. The popular image of a quantum computer is that of a machine that can magically handle an infinite number of variables, a machine that can tame the full complexity of the quantum world. But this is a misconception. A quantum computer does not solve problems by tracking all 2 to the power of 266 possible states of a 266-qubit system. That would be impossible, even for a quantum machine. Instead, a quantum algorithm is a cleverly designed process that uses the principles of superposition and interference to choreograph the evolution of the quantum state in such a way that the vast majority of the computational paths cancel each other out, leaving only the path, or paths, that lead to the correct solution. It is a process of radical quantum mechanical simplification. We are not taming the full complexity of the quantum world. We are finding a clever, simple, and manageable path through it. The problems that quantum computers are good at solving are not the ones that are irreducibly complex, but the ones that have a hidden, simple structure that can be exploited by a quantum algorithm. Factoring large numbers, for example, seems like a hard problem, but it has a hidden, periodic structure that Shor's algorithm is perfectly designed to find. The universe itself may be a quantum computer of infinite complexity, but our own human-made quantum computers will always be tools for finding the pockets of simplicity, the solvable problems that are hidden within that vast cosmic computation. This is not a pessimistic conclusion. It is a realistic one. It is a recognition of our own fundamental cognitive limits, and also of our own unique human genius. Our genius lies not in our ability to comprehend the infinite complexity of the universe, but in our ability to find the simple, beautiful, and meaningful patterns within it. We are the universe's pattern finders, its storytellers, its simplifiers, our science, our art, our technologies. These are all the products of this fundamental human drive to find order in the chaos, to find a signal in the noise. And our most advanced tools, from the James Webb Space Telescope to the next generation of quantum computers, are not tools that will give us a final, complete, and simple answer to the mystery of existence. They are tools that will allow us to ask new, deeper, and more beautiful questions. They are tools that will expand the horizon of our knowledge, and in doing so, will expand the horizon of our wonder. The universe's complexity is not an obstacle to be overcome. It is the very source of its beauty, its mystery, and its endless capacity for novelty. And our own human quest for simplicity is not a flaw. It is the very engine of our own unique and powerful form of understanding. In the vast tapestry of human knowledge, there lies a remarkable journey that began with a simple, audacious dream. Once it was said, in ages long past, that a single, brilliant mind could grasp the entirety of human understanding, could hold the sum of all knowledge within its grasp. Today, as we stand amidst an unprecedented explosion of information, a deluge of data that doubles in volume every few years, we might be tempted to wonder if such a grand, unified comprehension is still possible, or if it has become a relic of a simpler, more naive time. But this story is not about the quantity of knowledge, about the endless accumulation of facts and figures. It is about something far more profound, something that speaks to the very heart of the human quest for meaning, the quality of our understanding. Consider the cosmos that surrounds us, a universe of almost unimaginable scale and complexity. We know that there are hundreds of billions of galaxies, each containing hundreds of billions of stars. We have identified millions of species of life on our own small planet, with millions more likely waiting to be discovered. The sheer volume of information is staggering. To memorize the precise position and velocity of every planet, to catalog the intricate details of all 600,000 known species of beetles, this would be a task beyond the capacity of any single mind, or even any supercomputer we could currently conceive. But true understanding, the kind of deep, explanatory knowledge that is the hallmark of scientific progress, does not require this. It does not seek to grasp every particular, but to uncover the general, underlying principles that govern reality itself. It is the search for the simple, elegant rules that give rise to the complex, beautiful world we see around us. This quest for deep explanatory principles is perfectly illustrated by the revolution in our understanding of gravity. For millennia, humanity observed the motions of the planets, cataloging their positions with meticulous care. This was knowledge, but it was a descriptive, predictive knowledge. It could tell you where Mars would be in the sky on a given night, but it could not tell you why. Then came Isaac Newton, who, with his law of universal gravitation, provided a single, powerful principle that could explain not just the motions of the planets, but also the fall of an apple and the ebb and flow of the tides. This was a profound leap in understanding, but even Newton's theory, as powerful as it was not the final word. It described gravity as a mysterious force acting at a distance, but it did not explain the mechanism of this force. It was Albert Einstein who, with his general theory of relativity, provided the next, deeper layer of explanation. Einstein showed us that gravity is not a force at all, but is the very curvature of space-time itself. A dynamic, four-dimensional fabric that is bent and warped by the presence of mass and energy. Planets do not move in their orbits because they are being pulled by an invisible force from the sun. They move in straight lines through a space-time that has been curved by the sun's mass. This is a far more profound and beautiful explanation. It does not just tell us what will happen, it reveals why it happens, giving us an insight into the very structure of reality. And this is the crucial point: prediction alone, no matter how accurate, is not the same as understanding. Imagine, for a moment, that we possessed a magical oracle, a super predictor capable of answering any question about the outcome of any possible experiment. We could ask it, if I build this bridge in this way, will it stand? And it would give us a definitive yes or no. This would be an incredibly powerful tool, but it would not be a substitute for understanding. We would still need the principles of engineering, the knowledge of material science, the understanding of stresses and strains, to design the bridge in the first place. The oracle could tell us if our spaceship design would successfully reach the stars, but it could not design the spaceship for us. Understanding is what bridges the gap between knowing that and knowing why. It is what allows us to innovate, to create, to solve new problems that we have never encountered before. This is a pattern we have seen repeat itself throughout human history. The master builders of the ancient world, the constructors of the great cathedrals and pyramids, relied on a vast and complex set of rules of thumb, traditions, and accumulated experience, passed down through generations of apprenticeship. Their knowledge was deep, but it was also narrow, limiting them to familiar designs and incremental improvements. Today's architects and engineers, armed with a deeper, more unified understanding of the fundamental principles of physics and materials, can create structures that the ancients could hardly have imagined, from soaring, impossibly thin skyscrapers to orbiting space stations. This remarkable progress did not come from accumulating more rules, but from developing a smaller number of more general, more powerful, and more deeply explanatory principles that work everywhere, from the Earth to the Moon and beyond. As our knowledge grows, we witness a profound and beautiful paradox, a tension between two opposing forces. On the one hand, the ever-increasing breadth of what we know, the sheer volume of information pushes us towards specialization, the biologist, the physicist, the historian. The artist each delves deeper into their own specific corner of the vast tapestry of knowledge. It can seem as though the dream of a unified understanding is receding, that we are destined to become a species of experts who know more and more about less and less. But on the other hand, there is a countervailing force, a force that is, I believe, ultimately more powerful. It is the drive towards unification, the discovery that, as our understanding deepens, seemingly disparate phenomena are revealed to be different manifestations of a single underlying reality. And in this great intellectual battle between the fragmentation of specialization and the unification of deep understanding, depth is winning. Consider the history of mathematics. The ancient Babylonians and Egyptians had a vast and sophisticated knowledge of arithmetic and geometry, but it was a collection of separate techniques and rules for specific problems. The ancient Greeks, with their invention of the axiom. The Iambic method began the process of unification, showing how a vast number of geometrical truths could be derived from a small number of self-evident axioms. Today, modern mathematics, with its abstract structures of groups, fields, and topologies, contains within it all the understanding of these ancient systems, but in a far clearer, more powerful, and more unified form. The same story can be told in the history of cosmology. The Ptolemaic system, with its complex machinery of epicycles and deferents, was a masterpiece of predictive astronomy, but it was a collection of ad hoc rules, one for each planet. When Nicholas Copernicus placed the Sun at the center of the solar system, he did not just propose another theory, he radically simplified our understanding, revealing a deeper, more elegant underlying order. When Michael Faraday and James Clerk Maxwell unified the seemingly separate forces of electricity and magnetism into a single theory of electromagnetism, they showed us that apparent differences on the surface often mask a deeper, underlying unity. This same transformative process is happening today in the field of medicine. Where once doctors relied on a vast catalog of specific treatments for specific diseases, we are now beginning to understand the common underlying molecular and genetic mechanisms that connect seemingly different conditions, from cancer to heart disease to neurodegenerative disorders. This deeper, more unified understanding is what allows for the development of truly novel and powerful treatments. Therapies that target the root cause of disease, not just its symptoms. What we are witnessing across all these fields is not just the accumulation of knowledge, but its transformation. It is like the process of streams flowing into rivers and rivers flowing into a great, unified ocean. Our understanding of the world is becoming more coherent, more interconnected, more unified. We are not, as it might seem, moving further away from a state of overall comprehension. We are moving closer to it. This does not mean that we will one day know everything there is to know. The universe is likely to be infinitely complex, and there will always be new frontiers to explore, new mysteries to uncover. But it does mean that we are approaching a point where the structure of our knowledge itself is becoming more unified. We are beginning to glimpse the outlines of a truly fundamental theory, a theory that could provide a single, coherent explanatory framework for all of reality. This journey towards a more unified understanding is leading us towards something truly remarkable, something that has been the dream of physicists and philosophers for centuries, a true theory of everything. But this is not just a quest to unify the four fundamental forces of physics, as it is often portrayed. It is not just about finding the single, underlying principle that governs the dance of particles and waves. It is about something far grander, far more profound. It is about arriving at a unified understanding of reality itself. A framework that can accommodate not just the physical world, but also the nature of knowledge, of computation, and of life. This ultimate theory will not and cannot explain every single detail of existence. It will not predict the outcome of every human choice or the precise shape of every snowflake. That level of detail is likely beyond the reach of any finite explanation. But what it will do is show us how all our different explanations, from the laws of quantum mechanics to the principles of biological evolution, from the nature of computation to the growth of knowledge, fit together. It will reveal the deep underlying connections that bind all these different aspects of reality into a single, coherent, and comprehensible whole. It will be a theory that explains the reach of our scientific laws, the very comprehensibility of the universe itself. As we look up at the night sky, we are no longer just seeing points of light in the darkness. Through the lens of our current, partial understanding, we are already beginning to see a much richer and more interconnected reality. We see the complex, beautiful dance of gravity shaping the curvature of space-time. We see the life cycles of stars, from their birth in dusty nebulae to their explosive deaths as supernovae, a process that forges the very elements that make up our bodies. We see the fundamental forces of nature at play, the same forces that govern the interactions of particles in our laboratories, writ large on a cosmic scale. Each new discovery, each new piece of the puzzle, does not just add another isolated fact to our collection. It helps us to see the whole picture more clearly. It illuminates the connections. It reveals the deeper patterns. It brings us one step closer to a truly unified vision. We are living in a remarkable moment in the history of human thought, a moment where the depth of our knowledge is beginning to reveal the profound, underlying unity of all things. This is not the end of the journey of discovery. It is, in a sense, the end of the beginning. It is the dawn of a new way of seeing, a new way of understanding, a new way of being in the world. As we continue to explore the cosmos, both outward into the vastness of space and inward into the deep structure of our theories, we are not just gathering more information. We are uncovering the deep, beautiful, and intricate connections that bind everything together in the grand, cosmic dance of existence. In this journey towards a unified understanding, we are discovering that knowledge is not just about accumulating facts, but about seeing the patterns that connect them. Just as Einstein showed us that space and time are not separate, but are woven together into a single, dynamic fabric. Just as he showed us that matter and energy are not distinct, but are two faces of the same fundamental coin. Our growing understanding of reality is revealing itself to be a single, interconnected tapestry. Through this lens, the cosmos becomes not just a random collection of objects and events, but a coherent and deeply meaningful story. A story written in the universal language of mathematics and physical law. And as we stand at this unique vantage point, looking both backward at the long history of our quest for knowledge and forward to the mysteries that still lie ahead, we can see that our journey is not taking us further away from a state of ultimate comprehension, but for the first time in human history, bringing us tantalizingly, breathtakingly close. The future holds not just more knowledge, but deeper insight. Not just more information, but greater understanding. And in this cosmic dance of discovery, we are learning not just about the universe, but about the very nature of understanding itself. The vast, unending expanse of space offers us a landscape of mysteries that have captivated and bewildered humanity for generations. We have, in the grand scheme of things, explored only the tiniest, most infinitesimal fraction of its secrets, and yet, this exploration holds the key not just to understanding the cosmos, but to understanding the very process by which we make sense of the universe we inhabit. Science is our greatest and most powerful tool for unraveling these cosmic mysteries, a tool that is not static and rigid, but is itself shaped by a profoundly dynamic, iterative, and evolutionary process. What propels us forward in our quest for knowledge is not the comfort of certainty, but a relentless, insatiable drive to replace our current, incomplete answers with better, deeper, and more powerful explanations. The journey of scientific discovery is rarely a straightforward, linear march towards truth. It is more like the exploration of a vast, uncharted territory, a complex and interconnected web of questions, experiments, and theories that are constantly evolving, adapting, and interacting with each other. A new scientific theory often emerges not from a vacuum, but from a crisis. A moment when our current explanations fail to account for new, unexpected observations. Imagine being in a dark, sealed room, with only a few thin cracks of light streaming in. Each new discovery is like finding a new crack, letting in a little more light, revealing a small, new part of the much larger picture that lies outside. But each new sliver of light does not just provide answers. It also reveals new and more profound questions. The goal of every scientific endeavor, from the smallest laboratory experiment to the grandest cosmological theory, is not simply to collect and catalog observations. It is to develop better and deeper explanations for what we see, and perhaps even more importantly, for what we do not yet fully understand. The process by which we cultivate this knowledge, the very methodology of science, is an iterative and evolutionary one. It begins with the identification of a problem, a gap in our current understanding, a phenomenon that our existing theories cannot explain. This is the creative spark, the moment of curiosity that ignites the scientific process. From this problem, new ideas, new conjectured solutions, or hypotheses, are born. These are bold, imaginative, and often unjustified guesses about how things might really work. They are the raw material of scientific progress. But an idea, no matter how beautiful or elegant, is not enough. It must be subjected to the fire of rigorous testing and, most crucially, of criticism. In this process, weaker models, those that fail to solve the problem or that create even more problems, are discarded. Stronger, more robust, and more deeply explanatory models survive, but they do not survive unchanged. They are refined, adapted, and improved in the light of criticism and new evidence. This is not a failure of the process, it is its greatest strength. Paradoxically, this process of trial and error often requires us to backtrack, to abandon a promising but ultimately flawed idea, to admit that we were wrong. Progress in science is not always a straight forward march. It is a winding and sometimes recursive journey. It is a process of building, of testing, of demolishing, and of rebuilding, always on a stronger and more solid foundation. Criticism is the lifeblood of this scientific process. It is the selective pressure that drives the evolution of our knowledge, and contrary to the popular textbook image of science, the most important form of criticism does not come from experimental results. An experiment can tell us that a theory's prediction is wrong, but it cannot, by itself, tell us why it is wrong, or what a better explanation might look like. The most powerful and productive form of criticism comes from a direct, logical, and philosophical challenge to the explanations that a theory provides. When a new theory is proposed, it is not enough for it to simply fit the existing data. It must solve the problems that its predecessor could not. It must provide a deeper, more coherent, and more satisfying explanation of reality. A theory that cannot withstand this kind of rigorous, intellectual scrutiny, a theory that is vague or ad hoc, or that creates more puzzles than it solves, will ultimately be rejected. Not because an experiment has falsified it, but because it is a poor explanation. This brings us to a crucial aspect of what makes a scientific theory good. It must be falsifiable. A theory that can explain everything, that can be twisted and tweaked to fit any possible observation, is not a scientific theory. It is a dogma. A good scientific theory makes bold, specific, and risky predictions. It sticks its neck out. It exposes itself to the possibility of being proven wrong. It is this very vulnerability, this openness to being refuted, that is the source of science's strength. The theories that survive this relentless process of attempted falsification, the theories that withstand the fire of criticism, are the ones that we can provisionally accept as our best current understanding of reality. This view of science, championed by the philosopher Karl Popper, is a powerful antidote to the older and still common idea of inductivism. Inductivism is the notion that scientific knowledge is built by accumulating a large number of observations and then extrapolating a general law from them. It is the idea that we move from the specific to the general, from the observed to the unobserved. But this process is logically flawed, as the philosopher David Hume pointed out centuries ago. Just because the sun has risen every day in the past, we have no logical guarantee that it will rise tomorrow. The future does not have to resemble the past. Popper's solution was to turn this process on its head. Science does not proceed by induction, but by deduction. We do not start with observations. We start with problems, with bold, creative conjectures. We then use observation and experiment not to prove our theories, but to test them, to try and falsify them. The theories that survive this process are not proven to be true, but are corroborated, meaning they have, so far, withstood our best attempts to knock them down. They are our best and most resilient. Explanations. In this sense, science is driven not by the accumulation of data, but by the relentless pursuit of better, deeper, and more hard-to-vary explanations of reality. The evolution of our scientific knowledge bears a striking resemblance to the process of biological evolution by natural selection. Just as different species compete for resources in an ecosystem, different scientific theories compete for explanatory power in the intellectual landscape of a particular field. Some theories, like the dinosaurs, are dominant for a time, but are eventually driven to extinction by a new, more powerful competitor. Other theories adapt. They evolve. They are refined and modified in the light of new evidence and criticism. New theories are constantly emerging, born from the creative, mutational process of human imagination. And they are then subjected to the harsh, selective pressure of experimental testing and critical debate. The theories that survive and thrive are the ones that are fitter, the ones that are better suited to explaining the mysteries of the universe that eluded their predecessors. This evolutionary nature of knowledge ensures that science is not a static, dogmatic system of belief. It is a dynamic, open-ended, and constantly improving process. It is a process of trial and error, of conjecture and refutation, played out on a grand, intellectual scale. It is a process that mirrors the very creativity and resilience of life itself. Experimentation. In this evolutionary picture plays a crucial but perhaps secondary role. Its primary function is not to generate theories, but to act as a harsh and impartial judge, a selective environment that can kill off a bad theory. The most elegant and robust theories often make bold, surprising, and highly specific predictions, laying out scenarios that can be meticulously tested in the laboratory or through astronomical observation. A single, definitive experimental result that contradicts a theory's prediction can be enough to falsify it, to send it to the dustbin of scientific history. But a correct prediction, while valuable and often celebrated, does not and cannot definitively prove a theory to be true. There could always be another, as yet unthought of, theory that makes the same prediction but provides a deeper and more satisfying explanation. The true value of a correct prediction is that it lends a theory a greater degree of corroboration, of resilience. It is a sign that the theory is on the right track, that it has captured some real aspect of the structure of reality. But it is not the final word. The experiments are the stepping stones, not the destination. They are the fuel for the ongoing search for ever deeper and more comprehensive explanations. At the heart of all scientific progress, then, lies this relentless search for better explanations. A good explanation is not just one that accurately fits the observable data. A complex, ad hoc theory with enough free parameters can be made to fit any set of data. A good explanation is one that is also simple, elegant, hard to vary, and has a broad reach. It should explain more than it was designed to, making new, surprising, and testable predictions. Theories that fail to provide this kind of deep, explanatory power, no matter how accurately they might predict a particular phenomenon, will ultimately be seen as inferior, as mere phenomenological models, not as fundamental theories of reality. Science advances not simply by adding new facts to the great encyclopedia of what we know, but by fundamentally rewriting the encyclopedia, by replacing old, weak ideas with new, more powerful ones that offer a deeper and more profound insight into the mysteries of the universe. The search for knowledge, in this evolutionary and explanation-driven picture, is not a journey with a final destination. There is no ultimate, final truth with a capital T waiting for us at the end of the scientific road. Each new breakthrough, each new layer of understanding, does not lead to a final, complete answer. Instead, it opens up a new vista of questions, a new landscape of ignorance that was previously invisible to us. Today's best theory is simply tomorrow's stepping stone. The standard model of particle physics, for example, is an incredibly successful theory, but it leaves a host of deep questions unanswered. Why do the fundamental particles have the masses they do? What is the nature of dark matter and dark energy? How can we incorporate gravity into a quantum framework? Each of these questions represents a new frontier, a new problem that is driving the next generation of scientific research. This open-ended, unending nature of the scientific quest is not a sign of failure. It is the very source of its vitality and its excitement. It is what keeps science a living, breathing, and constantly evolving enterprise, rather than a static, dogmatic set of revealed truths. The universe, in all its vastness and complexity, is a landscape of infinite possibility. And the human mind, with its unique capacity for creative conjecture and rational criticism, is the perfect tool for exploring it. The cosmos challenges us to think beyond what we currently know. to question our most deeply held assumptions, to constantly strive for a better, deeper, and more unified understanding. It reflects back to us the very nature of science itself, a system built not on the solid ground of certainty, but on the dynamic, ever-shifting landscape of possibility. Each new discovery, from the subatomic to the cosmological, does not just add to our knowledge of the external world, it also deepens our understanding of ourselves, of our place in the cosmos, of the very nature of existence. As we explore the universe, we are also exploring the outer limits of human potential, the remarkable capacity of a small, curious primate on a tiny planet to grasp the deep, elegant, and often counterintuitive laws that govern the whole of reality. It is a journey that connects us to the universe in the most profound way possible, not just as its inhabitants, but as its conscious, questioning, and self-aware partners in a grand and unending dance of discovery. As we stand and gaze up at the night sky, at the vast, silent emptiness punctuated by the distant, twinkling lights of stars, we are confronted with one of the most fundamental questions of all. How do we know that what we are seeing is real? How can we be sure that the universe out there is not just an elaborate illusion, a grand and beautiful projection of our own minds? This is not just a question for late-night philosophical debates. It is a question that lies at the very heart of the scientific enterprise. Before we can even begin to build our theories of the cosmos, we must first have some confidence that there is a real objective cosmos to be theorized about. The first step on this journey is to understand the nature of explanations themselves. In science, an explanation is not a process of justifying a belief by tracing it back to some ultimate, infallible authority, whether that be a sacred text, a philosophical principle, or a direct, unmediated sensory experience. The long and often painful history of human thought has shown us that the search for such an ultimate, authoritative justification is a dead end. There is no such source. All our knowledge is, and always will be, conjectural, tentative, and open to revision. Instead, a scientific explanation is evaluated by its ability to solve problems, to make sense of the world, and to withstand rigorous criticism. An explanation does not need to be justified by its origin. It must justify itself by its performance. It must hold up under the relentless fire of logical scrutiny and experimental testing. This is the beauty and the power of the scientific method. It is not a quest for certainty, but a quest for the best, most resilient, and most deeply explanatory ideas. With this understanding of explanation in hand, we can begin to tackle the challenge of solipsism. Solipsism is the philosophical idea that only one's own mind is sure to exist. Everything else, the external world, other people, the entire universe could be nothing more than a dream, a figment of one's own, solitary consciousness. It is an idea that is logically irrefutable. You can never, with absolute certainty, prove that you are not the only mind in existence, and yet it is an idea that collapses under the weight of its own radical skepticism. To take solipsism seriously is to abandon the very possibility of knowledge, of science, of communication, of a shared reality. Our entire lives, our every action, our every thought, are predicated on the tacit assumption that there is a real objective world that exists independently of our own minds. Imagine trying to design and build a bridge while sincerely believing that the laws of physics and the properties of steel are just a projection of your own imagination. The endeavor would be not just impossible, but nonsensical. Scientific reasoning, by its very nature, is a rejection of solipsism. It is a collaborative, public enterprise that is built on the shared assumption that there is a real objective and comprehensible universe that we can all investigate, that we can all build theories about, and that we can all argue about. The very possibility of a scientific debate presupposes a shared reality to be debated. But even if we reject solipsism and accept the existence of an external reality, we are still faced with the challenge of observation and the problem of induction. How can we be sure that our senses are giving us a reliable picture of the world? And how can we justify our belief that the patterns we observe in the past will continue to hold in the future? The problem of induction, most famously articulated by the philosopher David Hume, is the puzzle of why we believe that repeated observations can lead to a general law. Just because every swan we have ever seen is white, we have no logical guarantee that the next swan we see will not be black. Just because an apple has fallen from a tree every single time in the past, we cannot, with absolute certainty, prove that it will do so tomorrow. The philosopher Karl Popper offered a brilliant and powerful solution to this long-standing problem. He argued that science does not and cannot proceed by induction. We do not build our knowledge by accumulating observations and then generalizing from them. Instead, science progresses through a process of conjecture and refutation. We start with a problem. We propose a bold, creative, and falsifiable explanation. And then we subject that explanation to the most rigorous tests we can devise, not to confirm it, but to try and refute it. The theories that survive this process, the ones that have withstood our best attempts to knock them down, are the ones we provisionally accept as our best current understanding of reality. Science is not about proving things to be true beyond all doubt. It is about eliminating error, about choosing the theory that has, so far, survived criticism better than its rivals. This brings us back to the question of reality itself. In this Popperian, explanation-driven view of science, reality is not an absolute, fixed concept. It is a judgment, a status that we confer upon those entities and phenomena that are part of our best, most resilient, and most deeply explanatory theories. The concept of gravity was once thought to be a mystical, occult force pulling objects downwards. Newton's theory gave it a new, more real status as a universal, mathematical force. Einstein's theory gave it an even deeper reality, reframing it as the curvature of space-time. What we consider to be real evolves as our explanations improve. But there is a practical common-sense aspect to this as well. The 18th century writer and wit, Dr. Samuel Johnson, famously responded to the philosophical idealism of Bishop Berkeley, who argued that matter does not exist independently of the mind, by kicking a large stone and declaring, "I refute it thus." His point was simple and profound. Reality is that which kicks back. If something can act upon us, if it can resist us, if its behavior requires an independent explanation that goes beyond our own internal, subjective experience, then we have good reason to consider it real. Galileo used this same principle to argue for the reality of Jupiter's moons. The light from those moons was not just a passive image. It was an active, physical entity that interacted with his telescope and his eye in complex and predictable ways. The moons kicked back, and in doing so, they asserted their own independent reality. Science applies this kicking back principle at every level of its inquiry. We believe electrons are real, not just because our theories require them, but because we can see their tracks in a cloud chamber. We can manipulate them with magnetic fields. We can use their flow to power our cities. They are not just theoretical constructs, they are entities that have a rich, complex, and autonomous set of effects on the world. This is the crucial distinction between a real entity and a mere illusion or a mental construct. A reflection in a mirror, for example, is complex, but its complexity is not its own. It is borrowed entirely from the object it is reflecting. It has no autonomy. A planet, on the other hand, has a vast and intricate complexity that is entirely its own, its geology, its atmosphere, its history. It exists and evolves independently of our observation of it. The more complex and autonomous an entity is, the more it kicks back, the more reason we have to consider it real. And this is where the evolutionary nature of our understanding comes full circle. Our scientific explanations do not just help us to uncover a pre-existing reality. They also change what we are capable of perceiving as real in the first place. The concept of a quantum field, for example, was once a strange and abstract mathematical tool. But as our theories have developed, and as we have seen its effects in a vast range of experiments, from the Casimir effect to the behavior of particles in accelerators, it has acquired a new and profound reality. It is now seen as the fundamental, underlying substance of the cosmos. This process is never-ending. The history of science is a history of our concept of reality becoming deeper, richer, and stranger. Dark matter and dark energy are the current enigmas on this frontier. They are currently hypothetical entities, inferred from their gravitational effects on the things we can see. But as our observations and our theories improve, they may one day transition from being mysterious dark entities to being accepted, and perhaps even understood components of our reality. The criteria for what we consider to be real are not fixed. They are open-ended and constantly improving, driven by our relentless quest for better, deeper, and more powerful explanations. It is a journey that is not about arriving at a final, absolute truth, but about a continuous process of peeling back the layers of reality, with each new layer revealing a world that is more complex, more beautiful, and more wonderfully mysterious than the one before. To understand the universe, we must first understand the nature of the tools we use to build our knowledge. And the primary tool of science is not observation, but explanation. This is a subtle but crucial distinction. The traditional view of science, known as inductivism, sees knowledge as arising from the patient accumulation of repeated observations. We see the sun rise in the east every day, and from this we induce the general law that the sun always rises in the east. But this is a deeply flawed picture of how science actually works. It does not explain why the sun rises, and it provides no logical guarantee that it will do so tomorrow. It is a form of prediction, not understanding. The philosopher of science, Karl Popper, provided a revolutionary alternative to this view. He argued that science does not progress by confirming theories, but by refuting them. We start not with observations, but with problems, with puzzles that our current understanding cannot explain. We then propose bold, creative, and highly specific conjectures, new theories that attempt to solve these problems. The crucial feature of a scientific conjecture is that it must be falsifiable. It must make risky predictions that, if they turn out to be wrong, would force us to abandon the theory. We then subject these theories to the most rigorous tests we can devise, not to prove them right, but to try and prove them wrong. The theories that survive this process of relentless criticism and attempted refutation are the ones that we provisionally accept as our best current knowledge. This is a process that is fundamentally about the growth of explanatory power. A good scientific theory is not just one that fits the facts. It is one that provides a deep, coherent, and hard-to-vary explanation for why the facts are the way they are. Newton's laws of motion did not just describe the elliptical orbits of the planets. They explained them as a consequence of a single, universal law of gravitation. This is the difference between a description and an explanation. And it is the search for these deep, unifying explanations that is the true engine of scientific progress. This leads to a profound and perhaps counterintuitive idea: science does not and cannot have an ultimate, unshakable foundation. The search for a source of absolute justification for our knowledge, a bedrock of truth, is a philosophical dead end. There is no such thing. All our knowledge is conjectural, fallible, and open to improvement. This may sound unsettling, like a recipe for radical skepticism, but it is, in fact, the very source of science's strength. It is because our knowledge is not built on a fixed, dogmatic foundation that it is able to grow, to adapt, to evolve. It is like climbing a mountain that has no summit. Each new step takes us higher, gives us a wider and clearer view, but also reveals a new, more distant horizon of what we do not yet know. The rationality of science lies not in its ability to prove its theories to be true, but in its relentless, self-critical process of seeking out and eliminating error, of constantly striving to replace our current good explanations with ever better ones. This evolutionary problem-solving view of science is beautifully illustrated by the Turing principle, a concept that connects the nature of computation with the very comprehensibility of the universe. The Turing principle, in its essence, states that it is possible to build a universal virtual reality generator, a computer that can simulate any physical environment that is allowed by the laws of physics. This has a profound implication. It means that the universe is, in a fundamental sense, knowable. The laws of nature are such that they can be understood, they can be modeled, and they can be simulated by a universal computer, which is itself a physical object within the universe. The human mind, with its capacity for creative conjecture and rational explanation, is, in this sense, a kind of universal explainer. The fact that we are able to create knowledge, to understand the deep and often counterintuitive laws of the cosmos, is not just a lucky biological accident. It is an intrinsic and perhaps even necessary feature of the kind of universe we inhabit. The universe seems to have a built-in capacity for being understood, and we are the vehicles for that understanding. This brings us back to the question of what it means for a theory to be true. In this fallibilist, Popperian view, we can never declare a theory to be definitively, absolutely true. The process of corroboration, where a theory survives numerous and severe attempts to falsify it, gives us a high degree of confidence in it. But it is not the same as proof. No theory is ever immune from the possibility of being superseded by a better one in the future. Newton's laws were considered the bedrock of physics for centuries, but they were eventually shown to be an approximation, a special case of Einstein's more general theory of relativity. And Einstein's theory, in turn, is likely to be superseded by a future theory of quantum gravity. This does not mean that Newton was wrong. It means that his explanation was of limited reach, and has now been subsumed into a deeper, more comprehensive explanation. This ongoing, open-ended process of refinement is the very essence of scientific progress. So, how do we act? How do we make decisions? In a world where we can never have absolute certainty, we act on the basis of our best available explanations. When we build a bridge, we use the principles of modern engineering, not because they are proven to be absolutely true, but because they are the best, most resilient, and most well-tested explanations we have for how to build a structure that will not collapse. The power of science lies not in its ability to provide us with final, dogmatic truths, but in its utility, in its remarkable ability to solve problems, to create new technologies, and to deepen our understanding of the world. It is a process that is driven not by a search for authority, but by a commitment to creativity, to criticism, and to the relentless, and ultimately joyful, pursuit of better and better explanations. And for those of us who look up at the stars and are filled with a sense of wonder, it is this very open-endedness, this promise of endless discovery, this constant striving for a deeper and more beautiful understanding of the cosmos, that makes the scientific journey so profoundly exciting. The ancient thinkers, from Aristotle to the natural philosophers of the Renaissance, often perceived living beings as being fundamentally and qualitatively distinct from the inanimate world. They saw in life a special spark, a vital force, or entelechy, an ability to initiate motion and to act with purpose that set it apart from the passive, mechanical world of non-living matter. But with the rise of modern materialistic science, this view was largely dismantled. Life, in the modern reductionist perspective, is often seen as being nothing more than a complex chemical process, a particularly intricate and self-organizing arrangement of atoms and molecules, governed entirely by the same universal physical laws that direct the motion of the planets and the decay of radioactive elements. And yet, even within this powerful and successful framework, life remains a profound and undeniable enigma. It is a phenomenon of such staggering complexity, such remarkable purposefulness, and such creative power that it seems to demand a special place in our understanding of the cosmos. Life is not just a passive result of the laws of physics. It is an active, knowledge-creating, and world-shaping force, a phenomenon that gives the universe a unique and dynamic character. Unlike the inert matter that makes up the vast majority of the cosmos, which drifts passively according to the laws of motion and thermodynamics, life acts with intention. It adapts, it learns, it evolves. It actively works to counter the relentless slide towards entropy, creating pockets of incredible order and complexity in a universe that is, on the whole, becoming more disordered. To understand life, therefore, is not just a problem for biology, it is a central problem for cosmology. We cannot hope to have a complete picture of the universe without acknowledging and accounting for the strange, wonderful, and perhaps even cosmically significant phenomenon of life. At the very core of what makes life so special is its intimate relationship with knowledge. Every living organism, from the simplest bacterium to the most complex human being, is an embodiment and a creator of knowledge. This knowledge is not just abstract information. It is functional, practical, and time-tested wisdom about how to survive, how to reproduce, and how to navigate the challenges of a particular environment. The most ancient and fundamental repository of this knowledge is the DNA molecule. Within the elegant double helix structure of DNA lies the genetic program of life, an incredibly intricate and densely packed code that stores the accumulated wisdom of billions of years of evolution. It is a blueprint, a recipe, a historical archive, a survival manual, all written in a simple four-letter alphabet. This molecular program is a stunning example of how knowledge can be physically instantiated and propagated through time. Through the twin processes of replication and mutation, life has mastered the art of both preserving its hard-won knowledge and generating the new variations that are necessary for future adaptation. But the creation of knowledge is not limited to the slow generational process of genetic evolution. In more complex organisms, another, much faster, kind of knowledge creation has emerged, the knowledge created and stored in neural systems. The human brain is the most complex and sophisticated knowledge-creating entity we know of in the universe. It is a biological computer of almost unimaginable power, capable of creating abstract models of the world, of generating novel explanations, of creating art, of contemplating its own existence. And the knowledge created by human minds is not just stored in our individual brains, it is propagated and amplified through the medium of culture. The memes, as the biologist Richard Dawkins called them, the ideas, the stories, the technologies, the scientific theories are a new kind of replicator, a new form of knowledge that evolves and spreads through human societies, allowing for a rate of adaptation and change that is orders of magnitude faster than genetic evolution. This dual system of knowledge creation, the genetic and the mimetic, gives life, and particularly intelligent life, a truly extraordinary power. It is the power to not just adapt to the environment, but to actively reshape it. And as we look to the future, the potential scale of this reshaping is almost limitless. Cosmologists and futurists speculate that a sufficiently advanced, intelligent civilization may one day be able to influence the cosmos on a galactic or even a universal scale. They might learn to harness the energy of entire stars, to build vast, self-replicating habitats, to re-engineer planetary systems, or even to influence the very laws of physics in their local corner of the multiverse. These are not just fanciful science fiction notions. They are plausible, long-term extrapolations of the knowledge-creating trajectory that life has been on since its inception. This perspective, which sees life as a fundamental, knowledge-creating, and world-shaping force, has profound implications for our understanding of the universe. It suggests that the long-term fate of the cosmos may not be solely determined by the blind, impersonal forces of physics like gravity and entropy. It may also be shaped, and perhaps even ultimately determined, by the purposeful actions of intelligent, living beings. On the one hand, life might seem to be an insignificant and fleeting phenomenon when compared to the sheer, overwhelming scale of the cosmos. The total mass of all the living organisms on Earth is a tiny, infinitesimal fraction of the mass of a single star. But to judge the significance of life by its mass is to make a category error. The true significance of life lies not in its physical presence, but in its influence, in its unique and remarkable ability to generate knowledge and to use that knowledge to create change. A single, well-formed idea, a scientific theory or a new technology, can have an impact that is vastly out of proportion to its physical substrate. It can change the course of history on a planet, and perhaps, one day, on a much larger scale. In this sense, life may be the most potent and significant phenomenon in the entire universe. It is the universe's own, built-in mechanism for generating complexity, for creating novelty, and for exploring the vast landscape of what is possible. This connects back to the Turing principle, the idea that the universe is fundamentally computable. Life, and particularly the human mind, can be seen as the universe's own homegrown universal computer, a system that is capable of understanding and modeling the very laws that gave rise to it. The fact that the universe has produced a system that can comprehend it is not just a lucky accident. It may be a deep and fundamental feature of its structure. The universe is not just a set of physical laws. It is a system that supports the creation and evolution of knowledge itself. This brings us to a beautiful and powerful vision. Life is not an anomaly in a dead universe. It is the universe's own creative edge. It is the leading wave in the cosmic story of increasing complexity and understanding. And we, as human beings, are at the forefront of this wave. The decisions we make, the knowledge we create, the future we choose to build, these are not just matters of local, terrestrial concern. They are events of potential cosmic significance. The future of life in the universe, the future of knowledge, the future of the cosmos itself, may depend, in some small but real way, on what we do next. This is a vision that is both humbling and inspiring. It is humbling because it reminds us of our deep connection to, and dependence on, the larger cosmic ecosystem. And it is inspiring because it endows our lives, our choices, and our quest for knowledge with a profound, and perhaps even ultimate, meaning. We are not just spectators of the cosmic drama. We are its protagonists, its authors, the agents through whom the universe is writing its own, and as yet unfinished, story. Mathematics is often perceived as a realm of pure, timeless, and abstract truth, a world of perfect forms and unshakable certainties that exists independently of the messy, physical world of our experience. But what if this Platonic vision is an illusion? What if mathematics is not a separate, transcendent reality, but is deeply and inextricably intertwined with the physical world? a product of the very same laws of nature that govern the stars and the atoms. This is a perspective that challenges our most deeply held beliefs about the nature of truth and knowledge, but it is one that is increasingly supported by our understanding of computation, physics, and the workings of the human mind. Take the very concept of a number. It seems like a pure abstraction, but the process by which we manipulate numbers, the process of calculation, is a physical one. It requires a physical system, an abacus, a piece of paper and a pencil, a digital computer, or the neural networks of a human brain to be carried out. And these physical systems are all governed by the laws of physics. The reliability of a mathematical proof is not just a matter of its logical consistency. It is also contingent upon the reliability of the physical processes that are used to check it. If the computer that runs a proof is subject to random quantum fluctuations that flip its bits, or if the brain that conceives of it is subject to the frailties of memory and attention, then the certainty of the proof is no longer absolute. It becomes a matter of physical probability. This idea is deepened by the work of the mathematician Kurt Gödel. His famous incompleteness theorems, published in 1931, delivered a devastating blow to the dream of a complete and provably consistent foundation for all of mathematics. A dream championed by the great mathematician David Hilbert. Gödel showed that in any sufficiently complex and consistent mathematical system, there will always be true statements that cannot be proven within that system. To prove them, you have to step outside the system and introduce new axioms. But this new, larger system will have its own, new unprovable truths, and so on, ad infinitum. This means that mathematics is not a closed, static, and complete system of eternal truths. It is an open-ended, creative, and constantly evolving enterprise. It requires the constant invention of new concepts, new axioms, new ways of thinking, and this process of invention is not a purely logical one. It is a creative, psychological, and ultimately physical process, carried out by physical beings with physical brains. The history of mathematics is a testament to this creative, evolutionary process. The axioms of Euclidean geometry, which were considered self-evident truths for over 2 millennia, were eventually challenged, leading to the development of the new, non-Euclidean geometries of Riemann and Lobachevsky. And these new, abstract geometries turned out to be not just mathematical curiosities, but the essential language needed to describe the curved spacetime of Einstein's general theory of relativity. The map and the territory, the abstract and the physical, are in a constant dynamic dialogue, each shaping and reshaping the other. This deep entanglement of mathematics and physics suggests that the Platonic view of mathematics as a separate, transcendent realm may be a beautiful, but ultimately misleading metaphor. Mathematical entities, the numbers, the shapes, the equations, do not exist in some heavenly, non-physical world. They exist, in a very real sense, in the physical world as patterns of information, as states of computational systems, as emergent properties of the laws of nature. This is a perspective that has been championed by the physicist David Deutsch, who argues that mathematics is a branch of physics. The truths of mathematics are not abstract, a priori truths. They are truths about the computational capacities of the physical world. The reason that 2 + 2 = 4 is not because of some abstract, Platonic law, but because the laws of physics that govern the behavior of a universal computer guarantee that any physical system that correctly performs the computation 2 + 2 will arrive at the physical state that we label 4. In this view, a mathematical proof is not an abstract, logical argument. It is a description of a physical process, a computation. And the validity of the proof depends on the physical possibility of performing that computation. This is a profound and radical shift in our understanding of mathematics. It takes it down from its Platonic pedestal and grounds it in the messy, contingent, and beautiful reality of the physical world. It also helps to explain the unreasonable effectiveness of mathematics in the natural sciences. A puzzle famously articulated by the physicist Eugene Wigner. The reason mathematics is so good at describing the physical world is not a miracle. It is because mathematics is the study of the computational structure of the physical world. They are two sides of the same, deep coin. This perspective does not diminish the beauty or the power of mathematics. On the contrary, it enriches it. It shows us that mathematics is not a sterile, static, and inhuman system of logic, but a living, breathing, and deeply human endeavor. A creative exploration of the very fabric of reality. The illusion of mathematical certainty, the idea that it provides an unshakable foundation for our knowledge, is a powerful and persistent one. But it is an illusion that we may need to let go of in order to arrive at a deeper and more authentic understanding of the world. What we are left with is not a failure, but a new and more profound appreciation for mathematics as a process of discovery, of explanation, of creativity, a process that is intimately and inextricably linked to our own physical and embodied existence as knowledge-creating beings in a knowable universe. The nature of time is perhaps the most profound, perplexing, and personal of all scientific and philosophical mysteries. We feel its passage in our very bones. We experience our lives as a continuous, flowing narrative, a journey from a remembered past through a fleeting present to an anticipated future. This experience of a flowing, moving now is so fundamental, so deeply ingrained in our consciousness, that it seems to be an undeniable feature of reality itself. And yet, when we turn to our best and most fundamental physical theories, this familiar, flowing river of time seems to evaporate into a strange and static landscape. This is the great paradox of time, the stark and seemingly irreconcilable conflict between the time of our subjective experience and the time of our physical theories. The common sense, intuitive view of time is that of a universal, cosmic river, carrying everything along in its current. The present moment is a special, privileged point in this flow, a moving frontier that separates the fixed, unchangeable past from the open, potential future. This is a powerful and deeply rooted metaphor, but it is one that is not supported by modern physics. Albert Einstein's theory of relativity, both special and general, delivered the first major blow to this classical picture. Einstein showed that time is not absolute, but is relative to the observer. Two observers moving at different speeds will experience time at different rates. For an astronaut traveling near the speed of light, time will slow down relative to an observer on Earth. This time dilation is not a psychological illusion. It is a real physical effect, confirmed by countless experiments. This means that there is no single, universal now. My now is not the same as the now of an observer in a distant galaxy. The concept of a simultaneous universal present moment is a casualty of relativity. Instead, Einstein's theory gives us a picture of a four-dimensional space-time, a unified fabric in which space and time are inextricably interwoven. In this picture, all of time past, present, and future is laid out, once and for all, in a single, static, four-dimensional geometry. This is the block universe view of time. In this view, there is no flow, no movement, no becoming. The past is not gone, and the future is not unreal. They are all just different regions of the space-time block. The dinosaurs are not extinct. They are just located in a different part of space-time. Our own future already exists, in the same way that a distant city already exists. We are just not there yet. The feeling of the flow of time, in this view, is a subjective illusion of our own consciousness, a trick of the mind that creates the impression of movement through this static landscape. But this is a deeply unsatisfying explanation for many. How can a universe in which nothing ever truly changes give rise to an experience that is so defined by change? This brings us to the quantum world, which adds another layer of strangeness and complexity to the mystery of time. Quantum mechanics, with its inherent indeterminacy and its focus on measurement, seems to reintroduce a distinction between the past and the future. A quantum system exists as a superposition of possibilities before a measurement, and as a single, definite outcome after a measurement. The act of measurement seems to be a moment of irreversible change, a point where the open potential of the future collapses into the fixed fact of the past. This has led some to suggest that the arrow of time may be rooted in this fundamental quantum process of wave function collapse. But the many worlds interpretation of quantum mechanics offers a different perspective, one that is remarkably consistent with the block universe of relativity. In the many worlds view, there is no collapse. The universe is a constantly branching tree of parallel realities, with each branch representing a different possible outcome of a quantum event. In this picture, all possible pasts and all possible futures exist simultaneously in a vast quantum multiverse. Our experience of a single linear timeline is just our journey through one particular branch of this infinite branching reality. The flow of time is the process of our consciousness moving from one snapshot of a particular branch to the next. The profound disconnect between the static, geometric time of physics and the dynamic, flowing time of our experience remains one of the greatest unsolved problems in all of science. It is a problem that touches on the deepest questions about the nature of reality, of causality, of free will, and of consciousness itself. If the future already exists, as the block universe model suggests, then what does it mean for us to make a choice? Is our feeling of free will just another illusion, our lives just the playing out of a pre-written script? The compatibility of free will with a deterministic or block universe is a long-standing philosophical debate. One possible reconciliation is to see free will not as a violation of the laws of physics, but as an emergent property of complex computational systems like our brains. We are free in the sense that our actions are not determined by external forces, but by our own internal, complex processes of deliberation and choice, even if those processes themselves are ultimately governed by deterministic physical laws. But the quantum multiverse offers an even more radical, and perhaps more satisfying, perspective. In the many worlds view, every choice we make may be real. When we are faced with a decision, the universe itself may branch, with different versions of ourselves living out the consequences of each possible choice in a different parallel reality. In this sense, we have a profound kind of free will. We are not choosing one path and eliminating the others. We are actualizing all possible paths, and our consciousness simply experiences the journey down one particular branch. This is a breathtaking and deeply humbling vision of reality. But what about time travel? The idea of moving through time, both to the future and to the past, is a staple of science fiction, and it is a concept that is not entirely ruled out by our current understanding of physics. Future-directed time travel is, in a sense, a proven fact. The time dilation of special relativity means that an astronaut traveling at near-light speeds is effectively traveling into the future of the Earth. Similarly, technologies that could slow down our biological processes, like suspended animation, would be a form of one-way travel to the future. Past-directed time travel, however, is a far more problematic and speculative concept. General relativity does allow for certain exotic solutions to its equations that contain closed, time-like curves, loops in space-time, that would allow an object to travel back to its own past. These could, in theory, be created by certain configurations of matter and energy, like a spinning, cylindrical universe or a traversable wormhole. But these solutions often require the existence of exotic matter with negative energy density, something that may not be physically possible. And even if a time machine could be built, it would immediately run into the famous paradoxes of causality, like the grandfather paradox. If you go back in time and prevent your own grandfather from meeting your grandmother, you would never be born, and therefore you could not have gone back in time to do so. This seems to be a logical contradiction. The many worlds interpretation of quantum mechanics offers a neat, if unsettling, solution to these paradoxes. If you travel back in time, you do not travel back into the past of your own universe. You travel to a different, parallel branch of the multiverse. You can change the past in that universe, but it will have no effect on the history of the universe you came from. The grandfather paradox is resolved, but at the cost of being forever stranded in an alternate reality. The mystery of time is a deep and multifaceted one. It is a puzzle that is not likely to be solved by physics alone. It will require a new, unified understanding that can bridge the gap between the objective, physical world and the subjective, conscious world, between the static landscape of space-time and the dynamic, flowing river of our own, lived experience. And as we continue to explore the universe, to push the boundaries of our knowledge, we are not just learning about the nature of the cosmos, we are also learning about the deep, strange, and beautiful nature of time itself. The quest to understand the fabric of reality, in all its richness and complexity, is not a journey that can be undertaken by any single discipline in isolation. It is an endeavor that requires a deep and fruitful collaboration between the different and sometimes seemingly disparate ways of knowing that humanity has developed. To truly grasp the universe, we need a unified, explanatory framework that can weave together the insights of quantum physics, of epistemology, of computation, and of evolution. These are the four fundamental strands of reality, and it is only by understanding how they are intertwined that we can hope to arrive at a truly comprehensive picture of the world. The first of these strands is quantum physics. It is the pillar of our modern understanding of the physical world, the theory that explains the fundamental mechanisms that govern the behavior of matter and energy. Quantum mechanics, and particularly its many worlds interpretation, reveals a universe that is far vaster, more complex, and more deeply interconnected than our classical intuition would ever lead us to believe. It shows us a reality that is not a single, definite state, but a branching, probabilistic multiverse, a symphony of intertwined possibilities. But physics alone, for all its power, cannot answer certain deeper questions. It can tell us how the universe works, but it cannot, by itself, tell us how we know how the universe works. This is the domain of epistemology, the second crucial strand. Epistemology is the theory of knowledge. It explains how our scientific theories are created, how they are tested, and how they evolve over time. It teaches us that knowledge is not a static, finished product, but a dynamic, open-ended process of conjecture, criticism, and refinement. Without a robust epistemology, we would be lost in a sea of competing ideas, with no rational way to distinguish between a good explanation and a bad one. The third thread in this grand tapestry is the theory of computation. Computation is not just about the processing of numbers in a digital computer. It is a deep and fundamental concept that describes how information is represented, transformed, and manipulated in any physical system. The laws of physics themselves can be seen as a form of computation, a set of rules that governs how the state of the universe evolves from one moment to the next. The Turing principle, which states that a universal computer can simulate any physical process, suggests a deep and profound link between the laws of physics and the laws of computation. It suggests that the universe is, in a fundamental sense, an information processing system. Completing this quartet is the theory of evolution. Evolution, in its broadest sense, is not just about the biology of genes and organisms. It is a universal principle that explains the emergence of complexity and adaptation in any system that has a mechanism for replication, variation, and selection. It explains how, from simple beginnings, intricate and purposeful-seeming design can emerge without a designer. We see this principle at work in the evolution of life, in the evolution of our scientific theories, and perhaps even, as some have speculated, in the evolution of universes within a multiverse. These four strands, quantum physics, epistemology, computation, and evolution, are the fundamental pillars of our modern understanding of reality. But they cannot be viewed in isolation. To do so is to see only a partial, and often distorted, picture. A reductionist approach that tries to explain everything in terms of physics alone will inevitably fail, because it cannot account for the emergent and equally fundamental realities of knowledge, of computation, and of life. These are not just complex applications of physics. They are fundamental principles in their own right, with their own explanatory power. A true theory of everything will not be a theory of physics alone. It will be a unified explanatory framework that shows how these four strands are interwoven, how they support and illuminate each other, how they come together to form a single, coherent, and beautiful fabric of reality. The quest for this unified, four-stranded understanding of reality is hampered by a number of deep and as yet unresolved explanatory gaps. These are not just areas where we lack data. They are areas where our current fundamental theories seem to be in conflict, or where they fail to provide a satisfying explanation for a key aspect of reality. The conflict between quantum mechanics and general relativity. The problem of quantum gravity is perhaps the most famous of these, but there are others that are just as profound. There is a deep explanatory gap between the theory of computation and the rest of physics. We know that information is physical, that it must be embodied in a physical system. But how does the abstract mathematical world of computation emerge from the underlying physical laws? What is the relationship between the bits of information and the its of physical reality? This is a question that touches on the deepest mysteries of both physics and information theory. Similarly, there is a gap between the theory of evolution and the other strands. Evolution by natural selection is a powerful explanation for the adaptation of life, but it does not, by itself, explain the origin of life, the transition from non-living chemistry to the first self-replicating organism. Nor does it fully explain the emergence of open-ended knowledge creation, the kind of universal explanatory power that seems to be unique to the human mind. Why has evolution on this planet produced a system that is capable of understanding the laws of the cosmos? This seems to be a phenomenon that requires a deeper, more fundamental explanation. And even within quantum mechanics itself, the most successful of our fundamental theories, there remain deep conceptual puzzles. The measurement problem, the nature of entanglement, the role of the observer. These are all areas where our current understanding is incomplete, where the theory seems to be pointing towards a deeper and stranger reality that we have not yet fully grasped. These explanatory gaps are not a sign of failure. They are the growing pains of a rapidly advancing science. They are the frontiers of our knowledge, the places where the next great revolutions in our understanding are likely to occur. But they are also a breeding ground for a philosophical stance that can be a major impediment to progress instrumentalism. Instrumentalism is the idea that scientific theories are not, and should not be, attempts to explain reality. They are merely instruments, tools for making predictions about the outcomes of experiments. In this view, a theory is judged not by its explanatory power, but solely by its predictive accuracy. Shut up and calculate is the famous and often misattributed motto of the instrumentalist. This is a tempting, and in some practical contexts, useful stance. But as a general philosophy of science, it is a dead end. It abandons the very thing that makes science so powerful and so exciting, its ability to provide us with a deeper understanding of the world. Prediction is a valuable and necessary part of science, but it is not its goal. The goal is explanation. A theory that can accurately predict the positions of the planets, but offers no explanation for why they move in that way, like the Ptolemaic system, is ultimately a scientific failure. A theory that not only predicts, but also explains, like Newton's or Einstein's, is a profound and lasting human achievement. The quest for a unified, four-stranded understanding of reality is a quest for explanation. It is the search for a single, coherent story that can make sense of the universe in all its multifaceted glory. It is a quest that requires us to be both bold in our conjectures and humble in the face of our own profound ignorance, and it is a quest that is driven by a deep and uniquely human the desire not just to observe the world, but to understand it. A truly unified understanding of reality, one that seamlessly weaves together the four strands of quantum physics: epistemology, computation, and evolution, would have profound and transformative implications for our future. It would not just be an intellectual achievement, it would be a practical one, with the potential to revolutionize our technology, our society, and our very sense of what it means to be human. Consider, for example, the future of artificial intelligence. Our current approaches to AI, while impressive in their own right, are largely based on a form of sophisticated instrumentalism. Machine learning algorithms are incredibly good at finding patterns in data and making predictions, but they do not, for the most part, create genuine, explanatory knowledge. A true artificial general intelligence, an AI with the same kind of creative, open-ended, and explanatory power as a human mind, will likely require a deeper, more unified understanding of the nature of knowledge itself. It will require a theory of artificial epistemology, a set of principles for how a computational system can generate and test new explanatory ideas. The development of such a theory would be a direct consequence of a deeper integration of the four strands. It would require us to understand how the process of knowledge creation, as described by epistemology, can be implemented in a computational system, as described by the theory of computation, that is itself grounded in the laws of quantum physics and has been shaped by a process of evolution. The creation of a true AGI would be a world-changing event, a moment when humanity transcends its own biological limitations and creates a new, and potentially far more powerful form of knowledge-creating intelligence. Or consider the future of medicine. Our current reductionist approach to biology has been incredibly successful, but it has its limits. A deeper, more holistic understanding of life as a phenomenon that is not just about physics and chemistry, but also about information, computation, and evolution, could lead to a new and far more powerful kind of medicine. Imagine therapies that are based not just on manipulating the molecular hardware of our cells, but on reprogramming their informational software. Imagine a medicine that understands and can work with the complex, adaptive, and evolutionary nature of disease. This would be a medicine that is not just about treating symptoms, but about restoring the deep, informational and computational integrity of the living system. This, too, would be a direct consequence of a more unified, four-stranded understanding of reality. But perhaps the most profound implication of this unified vision is its potential to reshape our own human worldview. The current fragmented state of our knowledge often leads to a sense of alienation and meaninglessness. The physical universe of science can seem cold, impersonal, and purposeless. The world of human values, of meaning, of consciousness, can seem to be a separate and ultimately illusory realm. A unified, four-stranded explanation of reality would heal this wound. It would show us how the physical, the epistemic, the computational, and the biological are not separate domains, but are different and equally fundamental aspects of a single, unified, and deeply meaningful reality. It would show us that we are not strangers in a dead universe, but are an integral and significant part of a cosmos that is, in its very nature, creative, knowledgeable, and evolving. It would provide a new and deeply rational foundation for a sense of wonder, of purpose, and of our own profound connection to the grand cosmic story of existence. The quest for a unified theory of everything is not just a quest for a final equation. It is a quest for a new way of seeing, a new way of being, a new and more complete understanding of who we are and why we are here. It is the most ambitious and the most important journey that humanity has ever undertaken.